Our hypothesis about this is that there is a lack of trust and transparency, as given credence by the very theme of our conference here in Trustworthy Analytics. And to solve this problem, we can turn to recent advances in AI, specifically in our field of explainable artificial intelligence, trying to answer the question of why behind a prediction made by a neural network. In the limited but emerging recent literature in explainable learning analytics, only one explainability method is often chosen, from SHAP for student dropout to a popular method LIME for student advising. But when we have our own downstream application, when we want to use a neural network and we want to decide which explainer to put on top of it, we don't know which one to choose. And to answer this question, our recent work at EDM 2022 implemented 5 different explainers across 5 different course settings for this prediction and found a very concerning result. So the graphic you see here is the most important image from that paper, which basically shows that instead of clusters using the same courses with the same students, you see clusters by explainability method instead, which means that even though our model is creating a prediction for a student, the different explainability methods that we are trusting to give a reason as to why are saying different reasons for those same students across different courses. So that begs a different question. Now we know that these explainability methods differ from each other. Is there any way to see which one is the right one to use by talking to perhaps human experts? So the objective of this paper is to build trust in these explainers with human expert validation. We look at the context of student success prediction, predicting pass-fail performance at the end of a MOOC or a blended flipped classroom course, and across 5 pairs of courses. So for each of these pairs of courses, there is a significant learning science difference between them that leads to differences in student behavior that we can then use to validate the explainers. And we use the 2 most popular explainability methods, LIME and SHAP, with both quantitative and qualitative evaluation. To get started, let's look at our data. Our data comes from our university in Switzerland, EPFL, across 3 different learning platforms, Coursera, edX, and Courseware. The 9 courses we choose have 20,000 enrollments with over hundreds of thousands of interactions. And these courses were chosen to highlight differences in learning behavior based in learning science literature. These 5 pairs are as follows. The first setting is MOOC versus flipped. So the curriculum stays the same, the professor stays the same, but the students that they're taught to and the modality in which they're taught are different for 2 pairs of courses. Then we have a difference in success rates, where the same course was taught once with a passing rate of 81% and once with a passing rate of around 7%. And a course on urban planning for African cities was taught to a French student population and an English student population. And lastly, we look at 2 math classes along the same lines with curriculum, along the same differences in student population, but the differences are basically that one has many more quizzes than videos and one has many more videos than quizzes. Now, why pick these 5 learning science differences? Those are the best ones we had access to. Of course, there are many more in literature, but we choose to use them as good examples for our case and to look across these areas moving forward, as there is a lot of text about these differences in student population across these approaches. Okay. Now the fun part, modeling. We are working on the task of student success prediction. For those, we derive 110 features from 9 different learning analytics papers. The data is of the scale of each student individually, their student behavior across that feature for a week, and looking at those weeks in general to make predictions for their eventual passing or failing in the course. For the architecture, we choose to use a standard architecture that has been used in a lot of different papers for this time series prediction task, a bidirectional LSTM with a sigmoid layer that eventually creates predictions, again based in previous work. And now the explanations. So now for these students, across all of these 9 courses, we have a model that predicts very accurately whether they're going to pass or fail. We now want to answer the question of why and compare that why across this difference of courses that we see. To do this, we use two methods. Line. Line creates local interpretable models on the scale of a single student. And we use SHAP. SHAP quantifies the marginal contribution of each feature to the prediction. These are both two different methods to identify feature importance scores for a certain prediction, so which features are more important than others. And the details of this are more thoroughly explained in these papers as well as several others. Okay, moving on to evaluation. In terms of quantitative analysis, we look at each course individually across the 9 courses. We look at each pair of courses and their contrastive differences. We look at the differences across explainability method, SHAP or line, and we look at the differences across metric. We choose 2 metrics to compare, specifically Jacquard similarity, which has to do with the difference between sets. Essentially, do certain features appear in some explanations over others? And Spearman's rank correlation, which has to do with the order of the features chosen for the explanation. This is particularly important because based on interventions, we can only intervene on a few features if we're trying to make a downstream correction of a failure prediction. And so making sure that the right features are near the top and found important across all methods is why we chose this metric. Okay. Now, this heat map represents a summarization of a lot of the results in the paper. Each row represents a course, so you can see the relationship of each course to every other course. And each quadrant represents the relationship of an explainer to another. And then each of these heat maps represents one of the metrics. And what we note immediately is these patterns along the diagonal. Oh, we're back. What we note immediately is these patterns along the diagonal. So what we see is that there are certain patterns by method and not by course, because the relationship we see are between SHAP and itself and line and itself, and not SHAP and line individually. We also see these kind of squares in the middle that represent similarities of MOOCs to each other and flipped classrooms to each other, giving us intuition that what it's doing is the right thing. And on the other graph, what we see is a very similar method as well. Specifically in that bottom quadrant, along the diagonal, we see a relationship between SHAP and itself. But the overall summary from these results is that there are significant patterns by method and not by course, which validates the result of our previous paper in a much more diverse course setting. Now we qualitatively examine what the top explainable features are across the course differences, so across the pairs of courses. And the caveat before I present these results is even though these courses are quite diverse and have a large student population, they are presented by one university in Europe. So it is important to not take these as generalized conclusions, but as one data point that we can use to build a further consensus in our field about what could be important and predictive. What we see is that early week behavior is more important for MOOCs than in other settings. We see that fine-grained video and problem click streams are really important for prediction in flipped classrooms. And we see that timely engagement and specific problem patterns could be intuitive across differences in student population. This has to do with our French versus English student population. And we see that the students who show anticipation, who do things early, are generally very performant across all of these settings. Cool. So now we've identified that these methods systematically disagree. So how can we still build trust in them? We turn to our human experts to validate these approaches. So, examining this problem, which human experts can we trust the most to build confidence in these explainers? We want those who are familiar with student success prediction, those who are familiar with teaching at the university level setting, and those who are familiar with MOOCs, online classrooms, flipped classrooms, and the like. So to find the best experts we could, we talked to 26 STEM university level educators for over 45 minutes or 1 hour each in semi-structured interviews to validate our explainability approaches. Now some demographic information about these professors. They are very diverse in geographic location from various regions all over the world. Because they are STEM professors, as is typical, 80% identify as male. In terms of age, the average age is 36 years with a high standard deviation, and all of them have strong MOOC expertise. They have often taught a course themselves. So, for these interviews, we asked them about which explanations they trust for various different parts of these courses and course settings. Now you see 3 explainers here. I've only told you about 2. So what is the third one? The third one is a confounder explanation. So essentially, we wanted to make sure that we didn't give the educators 2 only correct explanations that they would have a hard time choosing between. We wanted to design a confounder explanation based on counterfactuals that is designed to be explainability-wise objectively wrong, or hopefully not along the same lines as an accurate explanation. And they would pick between these 3. So the structure of this is for the MOOC versus flipped setting. We first tell an educator that you are teaching a course, and this is what your course looks like. It has these kind of assignments, these number of students, and your professor friend is teaching the flipped variation of your course. Then we ask them what features they think are important for determining student success or student failure, essentially to build a prior before we show them the explanations that the models have presented. Then we ask them to evaluate the explainers across both of these courses. Specifically, what we see is that we've abstracted away what method is there, and in fact, we shuffle them across both iterations, across both courses, so they have no way of knowing which method is the same. And then we want to develop some insights over the transition. So moving from MOOC to flipped, which features change the most to help student success? Which features change the most to predict student failure? Do you as an educator agree with these insights? Why or why not? And specifically, what actionable changes to your design, if you have this MOOC course, you're going to offer a flipped variation of it, what actionable decisions would you make based on these insights to your course? And we do this as well for the high versus low active learning setting, with more quizzes than videos. Great. So what are the results? We found that educators have diverse prior perceptions of what factors enable student success and failure. This is understandable given the difference in geographic region and various other aspects. But there were a few features that commonly showed up across these 2 themes. We saw that active participation in weekly videos was very important in the MOOC versus flipped course. We saw distinct problems answered in a quiz was very important in the flipped classroom setting. And educators chose to trust explanations that aligned with their prior belief. In over 45% of the cases, the explanation they chose had one of the features that they mentioned that they would choose as predictive of student success or failure when they were choosing which one they liked best. This, of course, led to significant disagreement amongst experts because they all had different prior beliefs. And only 3 of our interviewees chose the same method across both courses. And in fact, on average, about 30% of them chose the confounder explanation. What does this mean? Maybe it means that these explanations could lead to a lot of different, everyone has different prior perceptions and beliefs on student education. And our interviewees were definitely experts. This doesn't mean that they're bad at evaluating explainers. This means that based on their experience, these features turn out to be most important. So maybe no objective evaluation of explainers is possible. But the most interesting part was the last question, in actionable course design. So we did a humanities-style coding of their responses to try to identify what kind of suggestions they made. And what we saw were that a lot of them chose to redistribute problems in the course because some of our insights found that early in the course, people were going from problem to video, things like this, and later in the course, people were focusing more on problems. A lot of them suggested shorter videos. Specifically, in our active learning setting, we saw, well, in our active learning setting, what we saw was that there was a pause, play, pause interaction, and so a lot of people wanted shorter videos. And just to wrap up, while the suggested actions differed across experts, over 85% of them were able to use these insights for improving course design. To make these actions concrete, they wanted more granular insights on the scale of individual students or on groups of students to take these direct actions and integrate them back into the loop. So the main takeaways, quantitatively and qualitatively, there's maybe no one golden XAI approach for transparent predictions in education. But XAI does have potential to inspire ideas for improving course design. And perhaps our future work can work on designing neural networks with explainability at the core so we can trust the explanation because for this student, only these features were ever used. All of our code is available online, so please check it out. Thank you very much.
All right, so thank you so much, Vinitra. Again, I didn't introduce, but this is one of our best paper nominee for the conference, so good luck with that. And I think you are very good at explaining explainable AI. And I guess the audience also was able to get the same. So any questions for Vinitra?
Thank you. Thank you for your presentation. You're comparing the explainers, right? But what happened with the algorithm that's making the prediction? Have you tried comparing different algorithms using a single explainer?
That's a really great question. So the question was, have we considered comparing different model approaches instead of just comparing the explainers on a single model approach? I definitely think that's the direction of future work. To manage and understand the difference between explainers, usually keeping the model constant is step one, but I think this is a really important future direction.
Okay, there's a question online from Hashita Sharma. How do teachers' subjective interpretations of explainable AI insights impact the course design process, and how can this be accounted for in research studies?
Have subjective insights about what caused student success and failure. And this often chooses what explanation they find most useful or the one that they most trust. So to see how that impacts downstream course design, we first need to trust the explainers enough to put them in a study where they can make decisions for downstream students. So I think also this closing the loop, seeing how these suggestions can be implemented and seeing which ones improve learning outcomes the most is really important and perhaps, again, the next step.
Thank you for the amazing presentation. I'm just wondering for the 26th professor, right? Is there any similarity between similar discipline? Because they're from similar different discipline, right? So they would have different perceptions on the most predictive features. So have you considered that in your study?
Yeah, it's a great question. So of the 26 professors, 5 were used as a pilot to refine the study. And of those 21, most of them were computer science education professors, data science professors across various areas. So they were most suited to understand these kind of analytics. But I agree that it probably comes with a bias in comparison to a humanities professor or something like that about what they consider perceptions of student success, especially because one of the courses we used was a humanities course. But the ones that we had in the study were mathematics courses and programming courses, so these professors would be most suited for students of those areas.
So do you plan to use this kind of explanations for students? I think that may just be very similar to a question asked before, but I think this could be a thing that you may want to consider as well.
So the question was whether we could use these explanations for students?
Yeah, do you want to use these explanations for students as well?
So what we found, especially as through the qualitative analysis of the interviews, maybe explainers are more useful on the local scale of a single student than this kind of global scale course design approach. And that is work that we're hopefully doing to extend this work currently by doing some more interviews of local explanations that are stable and robust, and then seeing whether educators find even more trust in those than the course higher level explanations. The difference is that with MOOCs, with 6,000 students, 10,000 students, individual explanations are really hard for teachers to make any actionable difference. But in the scale of flipped classrooms and smaller classrooms that may be by student groups, this kind of insight could be very useful.
Finding related to selecting explainers that align with your belief, like prior beliefs. So I was interested in, is there any thought in like shaping that prior belief, like introducing either literature that kind of to inform, maybe like something about, hey, here's some best practices in design, or even maybe having people work in pairs or dyads where there actually is like different perspectives in the room like ahead of time before they see explanations. Is there any interest in that? Or
Yeah, I think it's a great idea, and I think in this community itself we've seen a lot of giving instruction and then seeing whether that actually impacts the result of what people learn. And I guess this explainer evaluation task is kind of a learning paradigm in itself. So it would definitely help, but we were hoping not to bias the outcomes of what the educators found important by showing them anything at all. But I do think it's an interesting next step to see if it would improve or reduce educator trust if they saw a blurb about, you know, in these classes, these kind of features are important, and then they have to choose features. Maybe they would.
Thank you so much. Okay.